Now we're going to talk about something called band theory, which has nothing to do with music. This is a more comprehensive model for metallic and covalent solids, and it comes out of molecular orbital theory. So what we understand is that atomic orbitals of atoms within a crystal can combine, and they're delocalized over the entire crystal. So we're not looking at individual atoms, we're looking at atoms within an atomic solid. And their atomic orbitals will combine and delocalize. So they're forming essentially molecular orbitals, just like we learned with molecular orbital theory. So when two atomic orbitals combine, you get a lower energy bonding orbital and a higher energy antibonding orbital. It will always be, though, that the lower energy bonding orbital is occupied and the antibonding orbitals are empty. As the number of atoms in the solid increases, the energy differences between the orbitals, the molecular orbitals, become smaller and smaller and smaller until it just really doesn't matter at all anymore. So here's an illustration of that. Here's one atom, lithium, just one atom, and here's its valence atomic orbital. When it combines and forms Li2, then it's going to make two molecular orbitals, and the lower one will be filled. There's one electron from each of these. They'll go into the lowest orbital, and the higher one will be empty. Let's skip that guy and go over here. And so here's lithium, and you're going to have lithium 4, and now you're going to end up with 4 orbitals, and the lower two, the bonding ones, are full, and the higher ones, the antibonding ones, are empty. As you increase this infinitely, these levels are getting closer and closer together. And so what you end up with in a reasonable sized crystal of lithium is that you've got occupied orbitals. These are called the valence band. So these are the bonding orbitals, and that's where the valence electrons are. That's why they call it the valence band. That's going to be full. And then right above that are the empty antibonding orbitals. This is called the conduction band. So what happens with electrical conductivity is that electrons will move from those valence orbitals, the highest occupied molecular orbitals, they'll move up just a tiny bit in energy to the empty molecular orbitals, the conduction band. And once they get up there, they can move around. In metals, there's no gap between the valence and the conduction bands. So there's essentially no difference in energy, and so the electrons can move into the conduction band, and metals are good electrical conductors. Metals are also good thermal conductors because thermal energy can be transported by the electrons. Remember, thermal energy is related to the kinetic energy of the particles. And so now these faster moving electrons can move around, and they can spread the thermal energy quickly throughout the crystal lattice. So here's a conductor. And this is yellow here. We can't really see it on the wall. Yeah. I'm going to make it yellow, just because I can. I think I can. And opacity. We'll see how that goes. That's the conduction band. There's the conduction band. There's the conduction band. That's just, looks like graffiti, whatever. There's no energy gap between the valence band and the conduction band. So here are all of those occupied bonding orbitals, and immediately above them, right next to them, no energy difference, is the conduction band, the antibonding. The reason that is because as you combine more and more orbitals into the molecular orbital that gets delocalized over the entire solid, the energies get closer and closer together. So when you've just got two atoms of lithium getting together, there are differences in the energy. When you've got three, the differences become smaller, and four, they become smaller. When you've got Avogadro's number of atoms, the difference is nothing. So metals conduct electricity because the electrons can very easily move into the conduction band. This is like almost like I think of this as being like a traffic jam, huge traffic jam. And this is the sidewalk, or maybe the shoulder of the highway. And these guys can just zip over there, and then they can zing along and move, and everybody down here is stuck. These guys can't move. This valence band is full. You can't move from one to the next. In a semiconductor, there is a small energy gap. In an insulator, there is a large energy gap. There's this big gap, and so in order for an electron to move into the conduction band where it can move around, it has to overcome this very large energy gap. And it just does not happen. In semiconductors, there's a small energy gap. And so they do conduct, kind of, right? Okay, there's got to be some questions, yes?
You were just saying, maybe I'm getting confused, but you were just saying in small energy atoms, there's a gap or something. You don't see a large energy gap here.
Okay, so let's go back to this one. When we put more and more atoms together and their orbitals combine to form molecular orbitals, the differences between these energy levels becomes less and less and less. Depending on the type of substance, there can be a gap in the middle, a separation between the antibonding and the bonding orbitals. In metals, there's no separation. In insulators, there's a big separation, and in semiconductors, it's in between. So the presence of the gap between the antibonding and the bonding is not reflective of the number of atoms in the solid, but on the kind of atom. So it's a very good question. Any other questions? Yes?
If conductors already don't have an energy gap, then what are the things we call superconductors?
That's a good question. I'd have to look that up. Yeah, I'd have to look that up. Superconductors. Any other questions that I might know the answer to? What's really neat about semiconductors is that we can control their conductivity. That's why they're so useful. We can make them more conductive or less conductive. And the way that's done is by doping them. So they add small amounts of dopants, and depending on what kind of doping element or substance you're using, you can get an N-type or a P-type semiconductor. An N-type semiconductor has extra electrons in the conduction band. So if we take silicon, which is a 4A element, how many valence electrons does it have? 4. And we put a little bit of phosphorus mixed in there, how many valence electrons does phosphorus have? 5. So there's going to be one more electron for each phosphorus atom that's put into this silicon. Well, those extra electrons are going to go into the conduction band because the valence band is going to be full. So the valence band is full, and now you've got a few electrons that are permanently, basically, in the conduction band, and so by adding a little phosphorus to the silicon, it will conduct electricity better. Those electrons in that conduction band are mobile, they conduct electricity. A p-type semiconductor has holes in the valence band. The valence band electrons can't move because it's like a traffic jam. It's gridlock. It's all full and there's nowhere to move. It's like, excuse me, could you move so I can get past? And they're like, no, I can't because the guy ahead of me won't move. Nobody's moving, so nothing moves. So in a p-type semiconductor, we could dope silicon with gallium. Gallium has 3 valence electrons. So we throw some of that in there, and that creates a hole in the valence band. Now there's a hole. So next to the hole, an electron can move into the hole, creating a hole behind him, and the next electron can move in. And so we can get some conduction in the valence band. So that allows the electrons to move. What they do with silicon chips is they make use of PN junctions, where you have a p-type semiconductor and an n-type semiconductor right next to each other. And that allows you to control the conductivity of the devices, and you can do just mind-boggling things with those sorts of silicon chips. They can act as diodes or amplifiers, but you get tiny spots that are p-type on one side and n-type on the other. There are semiconductors that are sensitive to pressure. And when you put pressure on them, they will conduct, and when the pressure comes off, they don't. And so you can use that to measure pressure. There are others that are sensitive to temperature and all sorts of fun things.